Hey there, have you ever stopped and looked at one of those huge, buzzing green utility boxes on your street corner, and then glanced down at the tiny little cube that charges your phone and just thought, how? How can they both be doing a similar job? Well, today, we're going to solve that exact mystery.
Have you ever wondered why transformers that can handle kilowatts of power need to be large and heavy, like mods, that is at 50, 60 Hz or low frequencies like that, while on the other hand, transformers for low power are small, like plug-in transformers that can barely charge your phone? It turns out there's real physics behind why more power means more size, and today we're going to derive it from the ground up with the math and concepts that make it completely understandable. So let's get into it.
What we're really looking at here is a tale of two transformers. They have the exact same job description, but as you can clearly see, they show up to work in, well, radically different packages.
Let's just put it side by side. Both of them are all about voltage conversion. The big guy on the pole takes thousands of volts from the power grid and steps it down for your house. The little guy takes the 120 or 240 volts from your wall and steps it way down to safely charge your phone. The function? Identical. The form factor, though, it's like they're from different planets. So what gives?
So section 1. What a transformer actually does. Okay, let's start simple. At its core, pun intended, a transformer is a machine that transfers power from one circuit to another through electromagnetic induction. Whoops! Actual transformers are rarely like this. Maybe CRT flybacks, yeah, but more often transformers are really like this. They have tight coupling of the windings around the same center. But anyway, the power equation is straightforward. This comes right from the definition of electric power, voltage, and current. Voltage is energy per charge multiplied by current, charge per second. That gives us energy per second, which is power. So, for both windings, we've got this. Except for AC, we use RMS values, of course, because their instantaneous values are constantly changing. If you need a refresher on that, feel free to jump to the section that explains it. See time codes below. We will move on shortly, but now let's take a break. It's been pretty heavy material. While you are recharging for the next section, I want to take a moment to share some fantastic news about an algebra course. Feel free to sit back, relax, and enjoy this fun little conversation that's going to follow. I recommend to stay tuned because there's going to be something extra about this whole math thing we are trying to tackle here, so...
Welcome back to the Deep Dive. Today we're doing a really quick look at what you actually need to know academically for serious work in electrical engineering, electronics, and physics research.
Right.
We're tracing this staircase of knowledge, starting with something familiar, Ohm's law,
Yeah.
VIR, and finding out what's holding the whole thing up.
Yeah, VIR is definitely where many people start. It's, perfect for basic circuits, lumped elements.
Simple stuff.
Simple stuff. But if you're aiming higher for complex research, sophisticated design, that equation, VIR, it's really just the welcome mat.
Okay, and that's where, based on the research we dug into, it gets interesting fast.
Yeah.
Because VIR, well, it doesn't stay simple.
Not at all.
If you want to deal with the real materials, fields changing over space, you
Yeah.
have to jump pretty quickly to the differential form of Ohm's law.
Exactly. And that's a big shift. You're suddenly not just looking at voltage across a whole wire. You're
Right.
looking at current density, electric field intensity,
Oh.
point by point in 3D space. And working with fields in 3D, you immediately run into Maxwell's equations. Can't avoid them. They're the fundamental rules for all electromagnetism.
Wait, hang on. From VIR, like basic circuit stuff, we're suddenly talking about the rules for the entire electromagnetic universe.
Yeah.
That feels like a massive jump.
It is, but it's totally necessary for anything advanced.
Yeah.
And that jump tells you exactly what you need to know beforehand.
Okay.
Because to even properly read Maxwell's equations, let alone use them, you absolutely have to understand vector calculus.
Vector calculus.
Right.
That's how you handle things with direction and magnitude in space, like fields.
Precisely. So Maxwell needs vector calculus. And vector calculus, well, that clearly needs basic calculus first. You can't do the fancy vector stuff without derivatives and integrals.
So we've gone from advanced EM theory back through Maxwell.
Yeah.
Back through vector calculus. down to basic calculus. We're almost at the ground floor now. What's the actual bedrock? What's supporting all of this?
And this is, I think, the most surprising bit from the source material, the ultimate foundation. It isn't some super complex math concept.
No.
It's an absolutely solid, like truly unshakable grasp of plain old school algebra.
That's it. High school algebra.
Right.
That's the secret the research points to. All that incredibly advanced engineering, the physics, it's built on algebra.
Provided you really know it.
Okay.
That's the key distinction.
Right. Yeah. We need to be clear. This isn't just, solving x plus 2 equals 5.
Not at all.
It's about being able to confidently manipulate complex, multivariable equations accurately, maybe under pressure, without making small mistakes. Is that it?
That's exactly it. The research really hammers this home. Algebraic manipulation is essentially the working language of calculus and vector analysis.
Ah, okay.
So if you're shaky on the algebra, even slightly, it creates this hidden bottleneck. You might think you're struggling with, say, a vector calculus concept in Maxwell's.
Yeah.
But the real problem is actually an algebraic slip-up you made a few steps earlier, and maybe you don't even realize it.
Wow. So if that foundation's weak, everything built on top is unstable, you basically have to fix the algebra first.
That's what the analysis suggests. Before tackling the advanced stuff, you need to ensure that algebra is absolutely rock solid. It's about readiness.
And the sources mentioned a specific way to address this.
They did. They highlighted the need for a dedicated approach. One example mentioned was a video series and member area. I think it was called Algebra Prime.
Algebra Prime, right?
Designed specifically to build that core algebra skill from the ground up, making sure you're truly ready for calculus and beyond. So you're not fighting with the basics when you need to focus on the complex ideas.
So the takeaway here seems pretty clear. If you're serious about this stuff, you now know where the most crucial leverage point is for your study time.
Yeah, prioritize that foundation.
It's kind of ironic, isn't it? The most basic thing is actually the most critical.
It really is. And, that brings up a final thought, something for you, the listener, to consider. Since all this high-level physics, this complex engineering, ultimately rests on mastery of basic algebra. Well, how often do really smart, highly trained experts get stuck on incredibly difficult theoretical problems? Only because, deep down, they're actually wrestling with an old, maybe unrecognized algebraic weakness, a vulnerability from maybe 10th grade that never got fully fixed.
That's actually a pretty unsettling thought, something definitely worth pondering.
Yeah.
Section 2, the heart of the transformer, the magnetic flux. So let's talk about the magnetic flux, the real reason why transformers need size. Now we need to refer directly to one of the Maxwell's equations, the Faraday's law. Here it is. Now, what is magnetic flux? If you need to refresh on that, it's a later section of the video. Feel free to jump around using timecodes. This formula is simply Maxwell's equation for induction, taking into account the number of turns. It's a simplified version of the more general differential vector rotor equation, but for transformers, we use the integral form. This is one of the most fundamental equations in all of electrodynamics. It tells us that the voltage across a winding is proportional to how quickly magnetic flux is changing through the core. Now, for sinusoidal AC, following through on this equation, you can actually derive the practical engineering expression for voltage. Here it is. We'll see how this exact formula is obtained at the end. After the recap, feel free to navigate there using timecodes for a detailed math breakdown. It's surprisingly simple and straightforward. Electricity, electricity. So section 3, core area and why it matters. We will now look at the core cross-sectional area, since it obviously contributes to the overall dimensions of the transformer. Magnetic flux phi flows through the core's cross-sectional area A, given a flux density B, which is measured in Tesla. See the section later explaining what 1 Tesla is. Feel free to jump around using the timecodes. So B is phi over A, and to avoid core saturation, we must keep B under circa 1.5 Tesla for silicon steel. And surprise, surprise, transformers use electrical steel, which is made of iron and silicon, not carbon like in regular steel. Why? Because silicon increases resistivity, reducing eddy current losses, and improves magnetic properties, making it ideal for transformer cores. For ferrites, the maximum allowance is like 0.3 Tesla. For reference, MRI apparatus use 1.5 Tesla for clinical systems, but high-field MRI can reach 3 Tesla or even up to 7 for research. Now the core cross-sectional area is obviously a cross. So the core is 3D, but we are interested here in just the 2D slice of the cross-sectional area. The area enclosed by the windings, if you will, is the area of the magnetic core limb through which the magnetic flux flows. It's perpendicular to the direction of the flux and is, like I said, 2D slice of the 3D core. So that's the area we're talking about here. Now let's rearrange the AC voltage formula to get A, the core cross-section. That's how we rearrange it. And this is what we get. So for a fixed B and frequency, core area must scale with voltage. And that's the first geometrical constraint. So as we can see, core area scales with voltage over frequency times number of turns. And assuming the frequency is known in advance and is fairly constant during operation, which is typically the case, A scales with V over N. So incidentally, it can be reduced with more turns. And it's good that we understood that the core cross-sectional area scales with the voltage, but the number of turns is kind of confusing. Everybody knows this formula, of course, the turns ratio. But we still don't know how many turns we need to use if we want to design a transformer. It doesn't give us. We may feel intuitively that making a one-turn primary for a transformer for the mains voltage, 110 or 230 volts, is not a good idea. It will blow up. Boom. Instant saturation. But anyway, or if we look at an existing transformer, we will not understand with this formula why it has the number of turns it has. So this parameter doesn't seem to be taking us anywhere right now. But thankfully, there is a clever way to get it out of the way and go straight to the current and power. So let's look at the current density, and the area of the space of the winding, the window sides. Section 4. What about current and windings volume? So understanding current density. Current density is the amount of current per unit area of a conductor. Ampere per square millimeter typically, or per square meter. It's a key concept in electrodynamics and Maxwell's equations, and it often simplifies logic and calculation and is more convenient for design. Now back to the voltage formula again. We will remember that it has frequency, number of turn, maximum inductance, and the core cross-sectional area. Now, how do we cleverly get away from the number of turns? Let's take the power instead of the voltage, which would be voltage times current. So let's multiply the right side by the current as well. And now let's introduce current density here. By going from current to current density, we'll be able to get away from the number of turns. So current is J times the area of the conductor. A single conductor in the first winding, let's say. And so we will see that we now have the conductor cross-sectional area times N. But isn't it the total area of the copper for the primary winding in the window? It is. It's the total area of the copper, the conductors, but only for the first winding, or the primary winding. And now we will notice that everything else is supposed to be the same for the primary winding and for the secondary, or secondaries. Really, the power is supposed to be the same, and power in, power out. We are ignoring the losses now, but they are typically, well, small enough, so the power can be assumed to be equal for simplicity. Frequency is the same, and Bmax is the same, and the core area is the same, and the J, the current density, is typically taken to be the same. In the optimal transformer, it is the same for the primary and the secondary, or a set of secondaries. So we have power balance, we have current density balance, and it will mean that the area of the conductors in the windings on the primary side and secondary side must be approximately equal as well. So we get the conductor area balance as well. So this N times conductor area is like 1/2 of the window area. Well, there is also this ampere turn balance, which is fascinating. It follows directly from the turns ratio equation, doesn't it? So number of turns in primary winding times current is equal to turns number of second winding and the current in that winding, which it must be so directly from the main transformer ratio. Now there is also this fill factor, because obviously not all space is taken by copper in the window, because copper is round and it has insulation and gaps and spaces and so on, so only a fraction is copper. And there is a factor that shows how much is copper, what percentage, what part is taken by actual conductors, which is typically what you see on the screen, 0.3 to 0.4 fill factor. So when we have the total area of the conducting material, we then gotta factor in this K, this fill factor. So that's the first thing. And the second thing will be that, well, with all these balances that we found out that exist, the power balance, the ampere turn balance, the current density balance, it follows that the conductor area must be approximately the same for primary set of windings and the secondary set of windings, or simply for primary and secondary, or primary and secondaries, which may be the case. Yeah, so the area of the conductors on the primary and secondary side must be approximately the same for a fully loaded transformer under normal conditions, which this mathematics describes. And so it follows that if we want to take now the window area, which is the space for all the windings, both primary and secondary, it's double the size of one winding area. So one winding area is 1/2 of the window area. That means we'll have to diminish by 2 times that area that we found out, and also factor in the coefficient for the filling factor, how much is taken by copper. And so what we are getting is this. We've gotten rid of the number of terms, we've got to the current density, we now have the window area, which is like this. So the 444 gets halved down to 222, and that's what we're getting. It's called output equation. That's the output equation. We now have the area product in there, both areas multiplied. Yeah, there it is, the area product. So there we go. Here we are. Here's the equation. We've gotten to it mathematically. That explains to us how the power scales up with area product, or vice versa. The area product must scale up with the power if everything else is constant. So the core area scales directly with the voltage over frequency times the number of turns. That's why high voltage, low power transformers can have a high number of turns, allowing for a relatively small core area. Now the window area scales directly with ampere turns over current density times fill factor. It's inversely proportional to current density and fill factor, and it's constrained together with the core area by the formula we've just discovered. Consider this: the core and window planes are perpendicular to each other. The cross-sectional area is oriented like this, and the window area like this. The core typically encompasses the windings from all sides to force as much magnetic flux to pass through the window area as possible, containing the flux and preventing leakage. This makes the transformer even bigger than the simple area product we've derived. Physical interpretation. Larger power means bigger dimensions. Mathematically, it's the product of the core area and the window area that gets constrained, which is quite curious. What can be more economical for the volume? Higher current density? Yes, but it must be kept below a certain limit to avoid overheating, just like the wiring in your house. About 3 amperes per square millimeter for copper, depending on the conditions. Higher frequency.
Well, the answer, the secret ingredient, if you will, that allows for this incredible shrinking act, all comes down to one single crucial concept: frequency. And understanding this is key. So, what even is frequency? In simple terms, the electricity coming out of your wall isn't a steady one-way street. It's an alternating current, AC. That means it's constantly flipping its direction, going back and forth, back and forth. Frequency is just how we measure how many times it does a full back and forth cycle every single second.
And this is where things get kind of wild. The power from the grid, the stuff the big utility transformer is dealing with, it cycles back and forth about 60 times a second. We call that 60 hertz. But inside your tiny USB charger, the electronics in there take that power and just skyrocket the frequency to 50,000 hertz, or even higher. I mean, that is just a mind-boggling difference in speed.
And that high-frequency advantage, it changes everything. It's literally the key that unlocks our ability to make all our electronics smaller and smaller. Let's dig into how that works. So here's the core principle, the big takeaway. The higher you can make the operating frequency, the smaller the transformer can be to handle the exact same amount of power. Think of it like this. If you need to move a bunch of water, you could use a big, wide, slow-moving pipe, or you could use a much smaller hose with the water moving at super high pressure. By making that electricity flip back and forth way, way faster, you can transfer the same amount of energy with a much, much smaller component.
And you see this principle in action everywhere. It's the magic behind something called switching mode power supplies, or SMPS for short. You can think of them as these tiny, super-fast, intelligent switches that create that high frequency we're talking about. They are the engines inside basically all modern power converters, and yep, they're the reason your phone charger isn't a total boat anchor.
Now, to make this high-speed magic happen, you can't just use the same old parts. Those massive utility transformers, they use heavy iron cores, which are great for low frequencies, but they're terrible at high speeds. Our modern gadgets use these tiny little things called ferrite core transformers. They're the unsung heroes specifically designed to work like a charm at these ridiculously high frequencies.
But, you know, in the world of engineering, there is almost never a free lunch, right? This incredibly elegant solution for making things smaller, well, it comes with its own brand new set of problems.
And this is a pretty big however. You see, just cranking up the speed isn't a simple fix. This high-frequency wizardry introduces a whole new host of engineering challenges. All of a sudden, you've got to worry about managing extra heat, you have to prevent all these high-speed signals from interfering with other electronics. It's a whole new puzzle. As the hardware gets smaller, the problem actually gets more complex.
Increased frequencies raise core losses and introduce high-frequency effects like skin effect and proximity effect, which need careful consideration. Higher magnetic flux density B, yes, but again, cores have delicate parameters that introduce constraints and limits, requiring careful selection and trade-offs. Higher fill factor. This is limited by heat dissipation issues, mechanical necessities, and the need for insulation. We will move on to the next section shortly, but before that I want to share something that might be very useful for you. Inspired by successful YouTubers making fortunes from their channels, then let's listen to this guy.
There has never been a better time than right now to start building your own online business that can make you money day in and day out. And the best place to start an online business right now is YouTube. Literally all you need is a phone or a laptop and you can make a ton of money with YouTube. My name is Matt Parr, and the super cool thing about this is that I started YouTube without ever even showing my face or stepping in front of a camera once.
Lots of people have already succeeded with their channels thanks to him. He also has two magic software tools that can help you accomplish more when it comes to making content. Links in the description. I've also prepared a video for you that talks more about that, as well as solutions to challenges like online security, financial progress, and additional creativity. There, we'll explore these topics with respect and care for you. I warmly invite you to watch this video when you get a chance. Either way, your support is the current that powers this channel. And now back to the show. And so the final section 5, before we get into the promised derivations and definitions, heat and cooling. So heat is a huge constraint. Core losses and copper losses turn into heat, and that heat must go somewhere.
We can obviously make transformers small enough to fit in the palm of your hand, so why are we also building them the size of a car? What is forcing engineers to scale these things up to such a mind-boggling size? Well, the answer, in a single word, is heat. Simple as that. In the world of power electronics, heat isn't just a little side effect, it's the ultimate villain. It's the #1 factor that dictates pretty much every design choice. And as we're about to see, it's the reason these things are so enormous. You see, here's the bottom line. There's a hard physical limit here. If you try to make a high-powered transformer too small without figuring out how to deal with the heat, it will literally cook itself from the inside out. The insulation will melt, the materials will break down, and the whole thing is just gone. The stakes are incredibly high.
So if we're going to defeat our enemy, we first have to understand it. Where is all this destructive heat actually coming from? Well, it turns out there are two main culprits that are basically turning a transformer into a giant oven.
First up, you've got wire heat. Engineers call this resistive loss. It's pretty simple. Think of a toaster. When you push a bunch of electricity through a wire, it gets hot. Same thing happens here. And second, you've got core heat, which comes from some really complex magnetic stuff happening inside the iron core.
Now, that core heat idea can be kind of tricky, but there's a fantastic way to think about it. Magneto-Friction. As the magnetic field is flipping back and forth 60 times a second, it's creating something that acts a lot like friction inside the metal itself. And all that friction, well, it generates a ton of heat. So how do engineers even keep track of all this? Well, they watch a key metric called current density. Basically, it's a measure of how much electricity is being crammed through a certain amount of wire. If that number gets too high, the wire heat, those resistive losses we talked about, goes through the roof, and you're heading straight for a meltdown.
Okay, so we know heat is the problem, and we know where it's coming from. Now for the main event. How does fighting this heat literally force transformers to get so big? This is where we run into this fascinating and totally inescapable trade-off that's baked right into the laws of physics.
The first thing you've got to do is attack the wire heat. The goal is pretty straightforward. You have to lower the electrical resistance of the miles of copper wire coiled up inside. Lower the resistance and you lower the heat. Simple, right? But how do you actually do that?
The solution is actually beautiful in its simplicity. To reduce electrical resistance, you just make the wires thicker. I mean, think about trying to drink a thick milkshake. It's way easier with a big, wide straw than a skinny one, right? It's the same idea. Thicker wires let the electricity flow more easily, which means less friction, and so less heat.
But, and this is the whole key to the puzzle, this simple solution kicks off an unbelievable chain reaction. Thicker wires obviously take up more space. That means the hole in the middle of the core where the wires go, it's called the winding window, it has to get bigger. And a bigger window means you need a bigger, heavier iron core to go around it. And just like that, the entire transformer is forced to get bigger and bigger in every direction.
But here's a really cool and kind of lucky twist in the story. As the transformer is forced to get bigger, something else happens. Its surface area gets way bigger too. And a larger surface area is much, much better at radiating all that heat out into the air. So it's this kind of happy accident where the solution, getting bigger, also helps solve the original problem in another way.
So we've talked about why they're so big, but that size is needed to handle some truly mind-blowing forces. To really appreciate what's happening inside that chunk of iron and copper, we need to talk about just how intense the magnetic fields are inside one of these things.
Now, to measure magnetic fields, we use a unit called the Tesla, named after the one and only Nikola Tesla. The technical definition is 1 Weber per square meter, but don't worry about the jargon. Let's just put this into a perspective that you can really feel. Okay, look at this. That tiny little bar on the left, that's the strength of the entire magnetic field of planet Earth, the one that makes our compasses work. Now, look at the bar on the right. That's the magnetic field inside a typical power transformer core. The forces being harnessed inside these simple boxes are thousands upon thousands of times stronger than our own planet's magnetic field. It's just immense.
So in the end, the reason power transformers are so big all comes down to a constant battle against heat, a battle that's refereed by the unchangeable laws of physics. Making wires thicker to fight heat starts a chain reaction that makes everything bigger, which luckily also helps get rid of that heat.
And now the bonus section, some derivations and definitions. So what is 1 Tesla? This is like you see, it's a magnetic flux density. 1 Weber per square meter. And some references, how much is Earth's field, MRI fields, and transformer cores. Oh, well, what about the magnetic flux itself? Well, today this concept is viewed through vector analysis. In vector analysis, a flux of a vector field is simply a measure how much of a vector intensity flows through a certain surface. So it's purely mathematical construct. If you have a vector field, you just envision a surface in this vector field and do some multiplications and additions to calculate this flux. So it's this kind of construct, but so the early 19th century pioneers of electricity might have envisioned that there is some real stuff flowing somewhere in space, you know, some magnetic fluid or something that really flows. So if you want an additional video on a vector analysis concept, that's okay. Now, regarding that formula for the transformer voltage, it's actually surprisingly simple. It is derived from the Faraday's law. If you just take this derivative for sinusoidal flux, if you follow through and substitute the things, noting that omega is this much, you'll get to this equation. 4 times 44 comes from 2 pi over square root of 2. Now the derivation of the RMS voltage is a bit involved, but you have it on the screen. Effectively, pun intended, it is peak voltage over square root of 2. It's also called the effective value. So the key insight is that it's the DC equivalent voltage that delivers the same power to a resistor. Thanks for watching to the end of this video. If you want more content like this, there is a playlist that should be popping up right now. Stay tuned for more. I've also made this free video for you with solutions for creativity, financial strength, and online security. I hope you'll enjoy this offer as well as all the others featured on my channel. And that concludes this video. Thanks for watching, and until next time, this is Hermalau Tube. My name is Konstantin, reminding you that your interest is the current that powers this channel.